Why is line voltage not 240 volt in a Y system when I have 120 volts on each phase? I mean, doesn't 120 plus 120 equal 240? Why is that? Well, this presentation is to try to show you what's involved and how we can prove that 208 volts is indeed the line voltage. This is not a presentation that you must know the ins and outs of, and neither is it a presentation that you will be assessed on. This is purely for your own interest. The first thing we need to clarify is that combining phase values requires an understanding of mathematical vector addition. The keys to remember that no two phases will be at 120 volts at the exact same time, and that's due to them having 120 degrees of separation and it being a AC circuit, which means we have, yes, an RMS value of 120, but that sine wave is continually rising and dropping. So, to combine or add phasor voltages together, we not only have to be aware of the magnitude or voltage, but we also have to have a good functioning application for the angle and the polarity. So when we look at VAN, or the A phase of a Y-connected three-phase source, 120 volt at 0 degrees, the A and N is actually quite important. And what I mean by that is that the AN actually indicates the polarity of the voltage. AN is quite different than voltage NA. And it may seem trivial, but that's actually one of the main hinging points that we need to wrap our heads around if we are to add two phase voltages together. Now, obviously, the 120 volt is the RMS magnitude, and the angle is the 0 degrees that we see on the phasor diagram. So the polarity is important because the combining of voltages requires that the polarity be in the same direction. And a great illustration of that is just the below batteries, where you can see that the polarity, positive, negative, having them in series, the voltage obviously adds together. Whereas if I were to reverse the connection, the voltage measured would be 0. Now in DC, we would get 0. In AC, you would get a slightly different number when you calculate it. So how then are we going to add these two voltages together? What I've shown here is that the vectors for the voltages that we have are actually in opposition to one another. I have 120 volts at 0 degrees and 120 volts at 240 degrees, but notice VAN, VBN, A to N, B to N. Notice how the arrows are pointing in the same direction. And what this then means is that if we were to add these two values, any number that comes out from a mode 3 calculation or an HV table would be completely meaningless. So the solution to this, we have to reverse the polarity of one of the phase voltages. So to correct this polarity, the letter reference must be reversed. And it gets a little bit weird. So now I have VAN and voltage NB. So I've changed the double subscript notation here to ensure that the polarity is in the same direction. Now, reversing the polarity has no effect on the angle, has an effect on the angle also. A new phantom or imaginary phasor is used. So where the heck is that? Well, this new imaginary phasor is right here. So there's my voltage BN, the original, 120 volt at 240 degrees. And we have changed the polarity artificially on paper so that we can effectively calculate this 208 value. Now, if I were to change the reference here, it means that the phasor itself is now in a different quadrant and 180 degrees, complete opposite direction. So we take 240 minus 180, and we're left with 60 degrees. So the switch from BN to voltage NB represents a 180-degree change for that phasor on the phasor diagram. Now, the new phasor is for calculation purposes only and is not present in the circuit and cannot be measured. So let's go through the process then. Now we have A to N, N to B. We have our 60-degree phasor here at 120 volts and our 0-degree phasor at 120 volts. And if we were to use either an HV table or mode 3, what you end up with is 208 volts at 30 degrees. Now, this process of phasor or vector manipulation proves why we have a root 3 correlation. The difference between the phase and line values, why we even get 208 volts, the quick shortcut is to simply use root 3 as opposed to a phasor addition process. It's also for phase and line current values in delta. And finally, it's also used for unbalanced delta line currents. So these areas we don't go into typically, but it goes to prove those three fundamental processes. Here's an example of each. We already know that on a Y system, the phase voltage is root 3 smaller than the line voltage. We know in a delta system that the phase current is root 3 smaller than the line current. But for this system, it's really hinging on the balanced delta arrangement. For a Y system, the voltage is not affected in any way by the system being balanced or unbalanced. In a delta unbalanced system, the only way that we can then determine what value these individual line currents are going to be is not through a correlation of simply root 3, because remember, root 3 is only relevant when the items are all balanced. In an unbalanced situation, we must ensure that we have a phasor addition which takes into account the different polarities that we see in the phasor diagram itself. And so this brings us to the end of our little expose on why line voltage is not 240 on a 120 volt 3-phase system.